7 Powerful function of resistor and its application. Resistors are fundamental components in electrical and electronic circuits, with several key functions that make them essential in various applications. Here are 7 powerful functions of resistors. Current limiting is one of the most crucial functions of a resistor in electronic circuits. Here's a deeper look at how this function works. Understanding current limiting. Concept. The primary role of current limiting is to prevent excessive current from flowing through a circuit, which could otherwise damage components, cause overheating, or lead to circuit failure. Ohm's law. The principle behind current limiting is based on Ohm's law, which states that equals times V equals I times R, where V is voltage, I is current, and R is resistance. By adding a resistor with a specific resistance value in series with the circuit, the current can be controlled and kept within safe limits. Applications of current limiting. LED protection. Purpose. LEDs are sensitive to current, and excessive current can quickly burn them out. Implementation. A resistor is placed in series with the LED to limit the current to a level that the LED can handle safely. For instance, if an LED operates safely at 20 milliamperes, a resistor is chosen to ensure this current flows when a specific voltage is applied. Battery protection. Purpose. To prevent excessive current draw from a battery, which can cause overheating or damage. Implementation. Resistors can be used to limit the current that is drawn from a battery, ensuring that the battery is not overstrained, especially in low-power devices. Sensor protection. Purpose. Many sensors and microcontrollers have current limitations, and excessive current can damage them. Implementation. Resistors are used in series with the sensor or input pin of a microcontroller to ensure that only the appropriate amount of current is supplied. Inrush current limiting. Purpose. When power is first applied, some circuits may experience a large surge of current, known as inrush current, which can damage components. Implementation. A resistor can be temporarily used to limit this surge until the circuit stabilizes, often in conjunction with a relay or a thermistor that changes resistance with temperature. Design considerations. Choosing the right resistor. To choose an appropriate resistor for current limiting, you need to know the desired current and the voltage across the resistor. Using Ohm's law, the resistance value can be calculated as equals R equals I, V. Power rating. The resistor must also have a sufficient power rating to dissipate the heat generated. The power dissipated by the resistor can be calculated using equals 2 times P equals I, 2 times R, or equals 2 P equals R, V, 2. Example calculation. LED example. Suppose you have a 5V power supply and want to limit the current through an LED to 20 milliamperes, 0.02 A. If the LED has a forward voltage of 2V, the resistor needs to drop 3V, 5V, 2V. Resistance value needed equals 3, 0.02 equals 150 omega, R equals 0.02 A. 3V equals 150 ohms. Power rating equals 0.02 times 3 equals 0.06. P equals 0.02 A times 3V equals 0.06 W. A 1/4 watt resistor would suffice. Current limiting through resistors is a fundamental practice in circuit design, ensuring both the protection and longevity of electronic components. Voltage division is another essential function of resistors in electrical and electronic circuits. Here's a detailed explanation of how voltage division works. Understanding voltage division. Concept. Voltage division refers to the process of dividing an input voltage into smaller output voltages using a series of resistors. The divided voltage is proportional to the resistance values. Series circuit. Voltage division occurs in a simple series circuit where 2 or more resistors are connected end-to-end. The total voltage across the series combination is divided among the resistors according to their resistance values. How voltage division works. When resistors 1, R, 1, and 2, R, 2, are connected in series across a voltage source, V, and the voltage across each resistor can be found using the following formula. equals times 2, 1 plus 2 V out equals V in times R 1 plus R 2 R 2 V in is the total input voltage across the series resistors. V out is the voltage across 2 R 2 1 R 1 and 2 R 2 are the resistance values of the two resistors. Applications of voltage division. Creating reference voltages. Purpose. Voltage dividers are often used to create reference voltages for various circuit components. Example. In an analog-to-digital converter, ADC, a voltage divider might be used to provide a reference voltage that scales the input signal to the appropriate range. Adjusting signal levels. Purpose. Voltage dividers can be used to scale down the voltage levels of signals to match the input requirements of other components. Example. If you need to feed a 5V signal into a microcontroller that only tolerates 3.3V, a voltage divider can reduce the 5V signal to 3.3V. Biasing transistors. Purpose. In transistor circuits, voltage dividers are used to set the correct biasing point. Example. The base of a bipolar junction transistor, BJT, is often biased using a voltage divider to ensure that it operates in the correct region, active region. Measuring high voltages. Purpose. Voltage dividers can be used to measure high voltages by scaling them down to a safer, more measurable range. Example. In multimeters, voltage dividers are used internally to allow the measurement of high voltages by reducing them to a level that the device can safely process. Power supply regulation. Purpose. Voltage dividers can provide a steady voltage level for low-power circuits. Example. A simple voltage divider can be used to derive a lower voltage from a higher one to power small circuits or devices. Design considerations. Resistor values. The choice of resistor values is crucial for accurate voltage division. The resistors should be chosen to provide the desired output voltage while ensuring that the current through the divider is appropriate for the circuit's needs. Loading effect. The voltage divider's accuracy can be affected if the load connected to the divider draws significant current. This is known as the loading effect. To minimize this, the resistors in the divider should be low enough in value to minimize the impact of the load, but not so low that they waste excessive power. Example calculation. Example circuit. Suppose you have a 12V power supply and want to obtain a 5V output using a voltage divider. Choose 1 R 1 equals 7k omega and 2 R 2 equals 5k omega. Using the voltage divider formula equals 12 times 5 omega 7 omega plus 5 omega equals 12 times 5. 12 is almost equal to 5 V out equals 12V times 7k omega plus 5k omega. 5k omega equals 12V times 12. 5 is almost equal to 5V. The output voltage, V out, is approximately 5V as desired. Benefits of voltage division. Simplicity. Voltage dividers are simple and cost-effective solutions for creating specific voltage levels. Versatility. They can be used in a wide range of applications, from simple reference voltage generation to complex signal conditioning. Voltage division is a powerful and versatile technique in circuit design, providing an easy way to manage and utilize voltage levels within electronic systems. Pull-up and pull-down resistors are crucial components in digital circuits, ensuring that inputs to logic gates or microcontrollers have a defined voltage level when no active signal is present. Here's an in-depth look at how they work and their applications. Understanding pull-up resistors. Purpose. A pull-up resistor ensures that a digital input pin reads a high, logic 1, state when no other component is driving the input. Without a pull-up resistor, the input might float, leading to undefined or fluctuating logic levels, which can cause erratic behavior in digital circuits. How it works. A pull-up resistor is connected between the input pin and the positive supply voltage, VCC. When no active low signal is applied, the resistor pulls the input to a high voltage level, typically the same as the supply voltage. When an active low signal is present, e.g., a switch to ground, the input is pulled to a low, logic 0 state, overriding the effect of the pull-up resistor. Understanding pull-down resistors. Purpose. A pull-down resistor ensures that a digital input pin reads a low, logic 0 state when no active signal is present. Without a pull-down resistor, the input might float, potentially picking up noise and causing unintended high readings. How it works. A pull-down resistor is connected between the input pin and ground, GND. When no active high signal is applied, the resistor pulls the input to a low voltage level, close to 0 V. When an active high signal is applied, e.g., a switch to VCC, the input is pulled to a high, logic 1 state, overriding the effect of the pull-down resistor. Applications of pull-up and pull-down resistors. Button debouncing. Purpose. Buttons and switches often generate noise when toggled, which can cause multiple transitions to be detected. Pull-up or pull-down resistors help ensure that the input pin reads a stable state when the button is not pressed. Example. A button connected to an input pin with a pull-up resistor ensures that the input reads high when the button is open and low when the button is pressed, connected to ground. Microcontroller inputs. Purpose. Microcontrollers often have input pins that need to be in a known state when not connected to other devices. Example. A microcontroller input pin might have a pull-down resistor to ensure it reads low when not connected, preventing false high readings due to noise or leakage currents. Communication lines. Purpose. In communication protocols like I2C, pull-up resistors are essential to ensure that data and clock lines are correctly biased when no device is actively driving them. Example. The I2C bus requires pull-up resistors on the SDA, data, and SCL, clock lines to ensure they default to a high state when no device is pulling them low. Logic gate inputs. Purpose. Logic gates with floating inputs can exhibit unpredictable behavior. Pull-up or pull-down resistors ensure that unused inputs are in a known state. Example. An AND gate with an unused input can have a pull-down resistor to ensure that the input is low, preventing unintended output states. Design considerations. Resistor value. The value of the pull-up or pull-down resistor should be chosen based on the current requirements of the circuit. Common values range from 1 kΩ to 100 kΩ, depending on the input characteristics and the speed of the circuit. Higher resistor value. Less current consumption but slower response time. Lower resistor value. Faster response but higher current draw. Internal versus external resistors. Many microcontrollers and logic devices have internal pull-up or pull-down resistors that can be enabled via software, reducing the need for external resistors. Example circuits. Pull-up resistor example. Suppose you have a push button connected to a microcontroller input pin. A 10 kΩ pull-up resistor is connected between the input pin and the 5V supply, VCC. When the button is not pressed, the input reads 5V, logic 1. When the button is pressed, the input is connected to ground, and the input reads 0V, logic 0. Pull-down resistor example. Consider a digital input pin that should read low when a switch is open. A 10 kΩ pull-down resistor is connected between the input pin and ground. When the switch is open, the input reads 0V, logic 0. When the switch is closed, the input is connected to 5V, logic 1. Summary. Pull-up resistors. Ensure a high logic level when no active low signal is present. Pull-down resistors. Ensure a low logic level when no active high signal is present. These resistors are fundamental in ensuring stable and predictable behavior in digital circuits, especially where inputs might otherwise be left floating and susceptible to noise or undefined states. Biasing is a critical concept in electronics, particularly in the context of transistors and other active components like diodes and operational amplifiers. Biasing involves applying a steady voltage or current to an electronic device to set its operating point, ensuring it functions correctly within its intended range. Understanding biasing. Purpose. Biasing establishes the proper operating point of an active component, such as a transistor, so that it can amplify signals or switch states effectively. The operating point, also known as the Q point, quiescent point, is the point on the device's characteristic curve where it remains when no input signal is applied. Types of biasing. Voltage biasing involves applying a constant DC voltage to a terminal of the device. Current biasing involves applying a constant DC current to a terminal of the device. Biasing in bipolar junction transistors, BJTs. For BJTs, biasing is crucial to ensure the transistor operates in the correct region, active, saturation, or cutoff, depending on the desired application. Active region. Purpose. The transistor acts as an amplifier. Biasing. The base emitter junction is forward biased, and the collector base junction is reverse biased. Example. In a common emitter amplifier, the transistor must be biased so that it operates in the active region, allowing it to amplify the input signal linearly. Saturation region. Purpose. The transistor acts as a closed switch. Biasing. Both the base emitter and collector base junctions are forward biased. Example. In switching applications, such as in digital logic circuits, the transistor is biased to enter saturation when turned on, ensuring it conducts fully. Cutoff region. Purpose. The transistor acts as an open switch. Biasing. Both the base emitter and collector base junctions are reverse biased. Example. In a digital logic circuit, the transistor is biased to enter the cutoff region when turned off, ensuring it does not conduct. Biasing circuits. Fixed bias circuit. Description. A resistor is connected between the base of the transistor and the power supply to provide a fixed base current. Advantages. Simple and easy to implement. Disadvantages. The operating point can vary with temperature and transistor beta symbol, variations. Collector to base bias. Description. A resistor is connected between the collector and the base. This configuration provides negative feedback, which stabilizes the operating point. Advantages. More stable than fixed bias. Disadvantages. Limited by the variation in collector current due to transistor parameter changes. Voltage divider bias. Description. A voltage divider network is used to provide a stable base voltage. This is one of the most common and reliable methods for biasing BJTs. Advantages. Provides excellent stability of the operating point, relatively insensitive to variations in beta. Disadvantages. Requires more components, resistors, than other methods. Emitter bias, self-bias. Description. A resistor is placed in the emitter lead, providing negative feedback to stabilize the operating point. Advantages. Good stability and simplicity. Disadvantages. The need for a large emitter resistor can reduce gain. Biasing in field effect transistors, FETs. For FETs, the biasing is somewhat different due to their operation based on voltage rather than current. Gate bias. Description. A resistor is used to set the gate voltage, controlling the current through the FET. Purpose. To ensure the FET operates in the desired region, e.g., saturation region for amplification. Self-bias. Description. A source resistor is used to provide feedback, stabilizing the operating point. Purpose. Common in JFET circuits, providing stability against variations in device parameters. Biasing in operational amplifiers, op-amps. For operational amplifiers, biasing typically involves setting the input and feedback conditions to ensure the op-amp operates correctly in its linear region. Purpose. Proper biasing ensures that the op-amp's output is centered within the supply rails, allowing maximum swing for the output signal. Importance of biasing. Stability. Proper biasing ensures that the active component operates stably over temperature variations and different operating conditions. Linearity. Biasing a transistor or FET in its active region allows for linear amplification of signals, which is crucial for analog signal processing. Efficiency. In switching applications, biasing ensures that transistors operate efficiently, minimizing power loss when switching between states. Example of biasing a BJT, common emitter configuration, circuit configuration, VCC, supply voltage, RB, base resistor for biasing, Re, emitter resistor for stabilization, RC, collector resistor to develop the output voltage. Design considerations. Choosing RB, the base current, IB, is calculated based on the desired collector current, IC, and the transistor's current gain. Beta equals beta IB equals beta IC. Setting V_B, the base voltage, VB, is set slightly above the emitter voltage, VB. E by approximately 0.7 V for silicon transistors. Operating point. The operating point is set by selecting RB and Re such that the transistor remains in the active region, allowing for linear amplification. Biasing is a foundational aspect of analog circuit design, crucial for ensuring that transistors, FETs, and other active components operate correctly and reliably in their intended applications. Impedance matching is a critical concept in electrical engineering, particularly in RF, radio frequency, circuits, audio systems, and transmission lines. The goal of impedance matching is to ensure maximum power transfer between a source and its load, as well as to minimize reflections and signal loss. Understanding impedance matching. Impedance, denoted as Z, is the opposition that a circuit presents to the flow of alternating current, AC, at a particular frequency. It is a combination of resistance, R, and reactance, X, and is usually expressed as a complex number. Equals, plus, Z equals R plus JX, where J is the imaginary unit. Matching impedance. The concept of impedance matching involves making the impedance of the load equal to the impedance of the source. When these impedances are matched, the maximum amount of power is transferred from the source to the load. Why impedance matching is important. Maximizing power transfer. Purpose. According to the maximum power transfer theorem, maximum power is transferred to the load when the load impedance, Z, L, is the complex conjugate of the source impedance, Z, S. For purely resistive circuits, this means equals Z, L, equals Z, S. Example. In an audio amplifier driving a speaker, impedance matching ensures that the amplifier delivers maximum power to the speaker, resulting in better sound quality. Minimizing signal reflections. Purpose. In transmission lines, such as those used in RF and microwave circuits, impedance mismatches cause signal reflections. These reflections can lead to standing waves, signal loss, and distortion. Example. In a coaxial cable transmitting an RF signal, if the impedance of the cable does not match the impedance of the antenna, part of the signal will reflect back toward the source, reducing the efficiency of the system. Preventing signal distortion. Purpose. Impedance mismatches can cause signal distortion, especially in high-frequency circuits. Matching impedance helps maintain the integrity of the signal. Example. In digital circuits, impedance matching on high-speed data lines ensures that signals are transmitted without distortion, preserving the integrity of the data. Techniques for impedance matching. Resistive matching. Description. Using resistors to adjust the impedance of the source or load. Example. In audio circuits, resistive attenuators, pads, are used to match impedance between different audio components, ensuring consistent signal levels. Transformer matching. Description. Transformers can match impedance by adjusting the voltage and current levels. The turns ratio of the transformer determines the impedance transformation. Example. In RF circuits, transformers are often used to match the impedance of antennas to transmitters or receivers, ensuring efficient signal transmission. LC networks, inductor-capacitor networks. Description. LC networks, combinations of inductors and capacitors, are commonly used for impedance matching in RF circuits. These networks can be configured as low-pass, high-pass, bandpass, or bandstop filters to match the source and load impedances at specific frequencies. Example. A pi network, a type of LC network, might be used to match the impedance of a transmitter to an antenna, optimizing the transmission of RF energy. Quarter-wave transformer. Description. A quarter-wave transformer is a transmission line with a specific length and characteristic impedance. When the length of the transmission line is 1/4 of the wavelength of the signal, it can match impedances between the source and load. Example. In microwave circuits, quarter-wave transformers are often used to match the impedance of different sections of a transmission line. Stub matching. Description. A stub, a short section of transmission line, is connected in parallel with the main transmission line. By adjusting the length and position of the stub, impedance can be matched at a specific frequency. Example. Stub matching is commonly used in microwave engineering to match the impedance of antennas or components in waveguide systems. Balanced to unbalanced transformer. Description. A balun is a device that converts between balanced and unbalanced signals and can also be used for impedance matching. Example: baluns are used in RF systems to match the impedance between a balanced antenna, like a dipole, and an unbalanced transmission line, like coaxial cable. Practical example of impedance matching. Example: matching an antenna to a transmitter. Problem: an RF transmitter has an output impedance of 50 ohms, but the antenna has an impedance of 75 ohms. Solution: an LC matching network or a quarter-wave transformer can be designed to match the 50 ohm source to the 75 ohm load, ensuring maximum power transfer to the antenna and minimizing reflections. Steps for matching. Calculate the reactance. Determine the required inductance, L, and capacitance, C values to create a matching network. Design the network. Configure the components in either a series or parallel arrangement to achieve the desired impedance transformation. Test the system. Measure the VSWR, voltage standing wave ratio, or reflection coefficient to confirm that the impedance is matched and that minimal signal reflection occurs. Benefits of impedance matching. Efficiency. Ensures that energy is efficiently transferred from the source to the load. Signal integrity. Preserves the quality of signals, especially in high-frequency applications. Reliability. Reduces the risk of damage to components due to reflected power or excessive signal distortion. Impedance matching is a vital technique in designing efficient and reliable electronic systems, particularly in communication, RF, and audio applications, where signal integrity and power efficiency are paramount. Filtering is a fundamental concept in electronics and signal processing, where it is used to selectively allow certain frequencies of a signal to pass while attenuating others. Filters can be implemented in various ways, including using passive components, resistors, capacitors, inductors, active components, operational amplifiers, or digital processing techniques. Types of filters. Filters are classified based on the frequency range they affect and their configuration. Low-pass filter, LPF. Purpose: allows frequencies below a certain cutoff frequency to pass while attenuating higher frequencies. Application: removing high-frequency noise from a signal or allowing the low-frequency components, such as the DC component in a power supply, to pass. Example: in audio processing, a low-pass filter can be used to remove high-frequency hiss from a recording. High-pass filter, HPF. Purpose: allows frequencies above a certain cutoff frequency to pass while attenuating lower frequencies. Application: removing low-frequency noise, like hum, or allowing high-frequency signals to pass. Example: in speaker systems, a high-pass filter might be used to block low frequencies from reaching a tweeter. Bandpass filter, BPF. Purpose: allows frequencies within a certain range to pass while attenuating frequencies outside this range. Application: isolating a specific frequency range from a broader signal spectrum. Example: in radio receivers, bandpass filters are used to select the desired frequency band for demodulation. Bandstop filter, notch filter. Purpose: attenuates frequencies within a certain range while allowing frequencies outside this range to pass. Application: eliminating a specific unwanted frequency, such as a hum at 60 Hz, in the US. Example: a notch filter might be used in audio systems to remove a particular interference frequency. All-pass filter. Purpose: passes all frequencies but alters the phase relationship between various frequencies. Application: used in phase-shifting circuits or to correct phase distortion in a signal. Example: in audio processing, all-pass filters can be used to correct phase shifts introduced by other filters. Filter design and implementation. Filters can be designed using different approaches depending on the application. Passive filters. Components: use resistors, R, capacitors, C, and inductors, L. Advantages: simple, no power supply needed, stable over time. Disadvantages: limited to lower frequencies, cannot amplify signals. Example: a simple RC low-pass filter consists of a resistor and capacitor in series, with the output taken across the capacitor. Active filters. Components: use operational amplifiers, op-amps, along with resistors and capacitors. Advantages: can amplify signals, more precise control over frequency response, capable of higher order filtering. Disadvantages: requires a power supply, potentially more complex to design. Example: an active low-pass filter might use an op-amp in an inverting configuration with an RC network to determine the cutoff frequency. Digital filters. Components implemented in digital signal processing (DSP) systems using algorithms. Advantages: highly flexible, can implement complex filtering operations, can easily change parameters in software. Disadvantages: requires analog to digital conversion, which can introduce latency. Example: a digital equalizer in audio processing software can adjust the gain at various frequency bands to shape the sound. Key parameters in filter design. Cutoff frequency, FC. The frequency at which the filter begins to attenuate the signal. In low-pass and high-pass filters, this is the frequency where the output power drops to half its maximum value, -3 dB point. Filter order. The order of a filter determines the steepness of the roll-off beyond the cutoff frequency. Higher-order filters have steeper roll-offs and greater attenuation of unwanted frequencies. Example: a second-order low-pass filter has a roll-off of 12 dB per octave, while a fourth-order filter has a roll-off of 24 dB per octave. Bandwidth. In bandpass and bandstop filters, the bandwidth is the range of frequencies that the filter affects. It is defined by the difference between the upper and lower cutoff frequencies. Q factor, quality factor. A measure of how selective a filter is, particularly in bandpass and notch filters. A higher Q factor means a narrower bandwidth, making the filter more selective. Example: a high Q bandpass filter will allow a narrow range of frequencies to pass, useful in applications like tuning radio frequencies. Attenuation. The reduction in signal amplitude as it passes through the filter. Measured in decibels, dB, attenuation is a critical parameter in determining a filter's effectiveness at blocking unwanted frequencies. Applications of filters. Audio processing. Filters are used to shape the sound, remove noise, and ensure that each component in a speaker system handles the appropriate frequency range. Telecommunications. Filters are essential for separating different frequency bands in communication systems, such as channel separation in radio and TV broadcasting. Power supplies. Filters are used to remove ripple from DC power supplies, ensuring a stable output voltage. Medical devices. In ECG machines and other medical devices, filters remove noise and interference, allowing for accurate signal measurement. Instrumentation. Filters condition signals from sensors, removing noise and enhancing the measurement accuracy. Example of a simple RC low-pass filter. Circuit configuration. Components: resistor, R and capacitor. C. Setup. The resistor and capacitor are connected in series, and the output is taken across the capacitor. Cutoff frequency calculation. The cutoff frequency, FC, is given by equals 1, 2, pi, FC equals 2 pi RC, 1. Example: 4 equals 10 omega, R equals 10 k omega, and equals 1 mu. C equals 1 mu f. The cutoff frequency is approximately 15.9 Hz. Operation. Signals with frequencies lower than 15.9 Hz pass through with minimal attenuation, while signals with higher frequencies are increasingly attenuated. Summary. Filtering is a versatile and essential tool in electronics, allowing engineers to control the frequency content of signals. Whether in audio processing, RF communication, or digital signal processing, filters are used to enhance signal quality, eliminate noise, and ensure efficient system performance. Heat generation in electronic circuits is a significant concern, as excessive heat can lead to reduced performance, component failure, and even permanent damage to electronic devices. Understanding the sources of heat generation and methods to manage it is crucial for designing reliable and efficient electronic systems. Understanding heat generation in electronic circuits. 1. Joule heating, resistive heating. Description. When electric current flows through a resistor or any conductive material, it encounters resistance, leading to the conversion of electrical energy into heat. This process is known as joule heating. Formula. The power dissipated as heat in a resistor can be calculated using equals 2 slash P equals I 2 R equals V 2 slash R where P is the power dissipated in watts, I is the current through the resistor in amperes, R is the resistance in ohms, V is the voltage across the resistor in volts. Example: in a resistor carrying 2A of current with a resistance of 5 ohms, the heat generated is equals 2 times 5 omega equals 20. P sad face 2A. 2 times 5 omega equals 20 W. 2. Power dissipation in semiconductors, transistors, and diodes. When semiconductors like transistors and diodes conduct current, they dissipate power in the form of heat, especially when operating in their active regions. Formula: the power dissipated in a transistor can be calculated as equals times P equals V C times I C, where V C is the voltage across the collector-emitter junction, I C is the collector current. Example: a transistor with equals 10 V C equals 10 V and equals 0.5 I C equals 0.5 A dissipates equals 10 times 0.5 equals 5. P equals 10 V times 0.5 A equals 5 W. 3. Switching losses in power electronics. Description: in power electronic devices like MOSFETs and IGBTs, switching losses occur during the transition between the on and off states. These losses are due to the simultaneous presence of voltage and current during the switching interval. Formula: the total power loss can be expressed as equals plus P loss, tongue sticking out, conduction, plus P switching, where P conduction is the power loss during the on state, P switching is the power loss during the switching events. Example: in a MOSFET operating at high frequency, switching losses can be significant and contribute to heat generation, particularly at higher frequencies. 4. Inductive and capacitive components. Inductors: heat is generated due to the resistance of the winding, copper losses, and core losses, hysteresis, and eddy currents. Capacitors: while ideal capacitors do not dissipate power, real capacitors have equivalent series resistance, ESR, leading to heat generation during charge and discharge cycles. 5. Leakage currents. Description: leakage currents in capacitors, diodes, transistors, and other components result in small but continuous power dissipation, contributing to heat generation. Example: leakage current in a reverse bias diode or an off-state transistor can cause heat, particularly in large-scale integrated circuits. Managing heat generation in electronics. Thermal management techniques. Heat sinks: metal components attached to heat-generating devices to increase surface area for heat dissipation. Used in power transistors, CPUs, and power supplies. Fans and forced air cooling. Fans are used to move air over components, enhancing convective heat transfer. Thermal interface materials, TIMs. Materials like thermal grease or pads are used to improve thermal conductivity between components and heat sinks. Circuit design considerations. Component selection. Choosing components with lower power dissipation, such as low RDS on MOSFETs, can reduce heat generation. Derating. Operating components below their maximum rated voltage and current to reduce power dissipation and extend their lifespan. Power distribution. Distributing power across multiple components to prevent excessive heat in any single component. Packaging and enclosure design. Ventilation. Designing enclosures with vents or fans to allow for adequate airflow, preventing heat buildup. Material selection. Using materials with high thermal conductivity for enclosures to facilitate heat dissipation. Thermal simulation and analysis. Software tools. Use thermal simulation software to model heat distribution in electronic circuits and optimize component placement and cooling strategies. Thermal imaging. Infrared cameras can be used to identify hotspots in a circuit, allowing for targeted cooling measures. Energy efficiency. Power management. Implementing power management techniques such as dynamic voltage scaling and sleep modes can reduce overall heat generation in electronic systems. Efficiency optimization. Designing circuits and systems with a focus on energy efficiency minimizes unnecessary power dissipation, leading to less heat generation. Examples of heat generation in electronics: computers and CPUs. Challenge: CPUs generate significant heat during operation, especially under heavy processing loads. Solution: heat sinks with fans, liquid cooling systems, and thermal throttling, reducing CPU speed when overheating, are commonly used. Power amplifiers. Challenge: power amplifiers in audio systems or RF transmitters can dissipate large amounts of power as heat. Solution: large heat sinks and active cooling are used to manage heat, ensuring stable operation. LED lighting. Challenge: high-brightness LEDs generate heat, which can degrade performance and reduce lifespan. Solution: thermal management with heat sinks and proper PCB design to distribute heat efficiently. Consequences of poor heat management. Thermal runaway. In semiconductors, excessive heat can increase leakage currents, leading to further heat generation and potential device failure. Component degradation. Prolonged exposure to high temperatures can accelerate aging and reduce the lifespan of electronic components. Reduced performance. Overheating can lead to thermal throttling, where the performance of a device is intentionally reduced to prevent damage. Safety hazards. Excessive heat can cause burns, fire hazards, and in extreme cases, explosions, especially in batteries and power electronics. Heat generation is an inherent aspect of electronic circuit operation, but with careful design and effective thermal management strategies, it can be controlled to ensure reliable and efficient performance of electronic devices. These functions highlight the versatility and importance of resistors in a wide range of electrical and electronic applications.